So we'll finish up what's left in lecture 4 and get started on. We're going to start a series of hands-on lectures. I think it's about 7 lectures where we all open up our Google Colab and start building LLMs from scratch. And today's exercise is going to be building tokenizers and word embeddings, which is going to be the very first step. And please raise your hand if you have ran the Colab exercise and imported the class materials into your Google Drive. Okay, so how many of you have not done the Colab exercise and have not uploaded the materials? Okay, so we still have time because we need to cover the lectures. So I guess in the background, please do so immediately because I'm going to assume everything's imported and set up and ready to go. Okay? So download your zip file from ETL, import it into your Google Drive, and set up Colab and make sure you can connect to the Colab. Okay? How many of you have never used Colab before? Only one person? How many of you used Colab before? Oh, okay. Almost everyone. All right. How many of you know how to use Python? Okay, there are about 10 people who don't know how to use Python. Anyways, that's a prerequisite for the class. So this class, unfortunately, assumes that you know how to use Python and somewhat familiar with NumPy syntax. Otherwise, it's really easy to learn, so you can teach yourself. One caveat I should also mention is these days Colab has a feature where you can enable generative AI to help you write code. I strongly suggest you do not use that feature because you're not going to learn anything. I tried it and it's so good, and you just press tab and it automatically gives you an answer. So at least during the class, please do not use generative AI. Because the point of these lectures is for you to think on the spot and build LLMs from scratch. If you use generative AI and just press tap, 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 you're not going to learn anything. Otherwise, there's no point. All right, so let's get started. Let me briefly just review what we discussed last time. So in lecture 4, we talked about various techniques and models and model architectures in order to deal with sequential input data. So as opposed to a single static input, such as a single image or a single natural language sentence, what if you have sequences and sequences of input data, such as PDF files of, say, 1,000 pages? Or you want to process individual frames in a YouTube video. And it has variable length per each data point, right? And you need a special architecture that can deal with arbitrary length sequential data. So RNNs were simplest in form. The idea was use this weight shared matrix W that once you define some form of internal state HT, upon receiving the current sequence input XT, you update your HT. And based on your HT, you can decide if you want to output a YT, which is a prediction that corresponds to XT. which may or may not make sense depending on your task or application. For example, if you're dealing with, say, machine translation, for example, it might not make sense to immediately output your translation upon seeing only fragments of the input, because in natural language, the word ordering and structure varies a lot among different languages. For example, in Korean, there's a saying, 한국말은 끝까지 들어봐야 한다. So you need to wait until the end to hear the verb. So once then, you compress all the knowledge into the final internal state, and then you can start decoding its translation in another language. Okay? And then we talked about very, very basic language modeling at character level, where you have a predefined vocabulary or a dictionary, and you turn it into a one-hot embedding, and you apply some matrices, and you have some unnormalized score where you can sample according to that, and it gets fed back into the next input, and etc. And we have these special tokens called beginning of sentence and end of sentence, where it indicates upon receiving this, this is the beginning of a decoding sequence for a sentence, and end of sentence token, it ends the sentence. So, for example, if you're running inference with this, as soon as you encounter end of sentence, you finish that sentence, and you might decide to generate another sentence, for example, or end generation there. And we talked about the gradient flow problem in RNNs. So for inference, you keep multiplying. And I think I updated the lecture notes. I didn't bring it here today, unfortunately, but this normalization happens once you have finished running forward computation and backward computation. So once you finish forward and backward, you normalize it by the gradient if the gradient norm is above some threshold to make it small again. But if you keep multiplying W and the largest singular value of the weight matrix is less than 1, you keep multiplying small numbers. By then, once you have finished forward backward computation, it's too late to normalize, because the signal is going to be lost during forward pass and backward pass. So what's the alternative? We talked about LSTMs. Here, as you notice, we have this new state called cell state. Here, there's no matrix multiply. It's just element-wise gating or element-wise multiplication. So the signal gets propagated across time more easily here. And you only decide to add in to the cell state through matrix multiply. So here, at least in the cell state, there's no problem of repeated matrix multiplies. Okay, so, and we talked about attention. So, for example, if you have an extremely long sequence, is it really a good idea to condense all that knowledge into a single small vector? You might lose too much information from this process. So at least in the decoding phase, if you think about inference, you might want to have explicit architecture that supports explicit reference to all the previously processed tokens. And that's where attention comes in. So here, upon receiving input, axis, you have these parameters, key, value, query matrices, multiply them, and compute these activations called query vector, key vector, value vector. And you take query and key outer product, and you get this similarity matrices, which is upsized number of tokens by number of tokens. And upon computing the similarity, you normalize it by hitting with softmax. And once you have these attention weights, then you can multiply by the value activations or value vectors to produce output. And that's a single self-attention layer. All right, so and we're going to go deeper about this, but you want it to be dependent on the order in which it's inserted into the module, because order is important. But as is, it's permutation equivariant, so you might want to add something that's sensitive to the location, relative location in the sentence, and that's called positional encoding. And we're going to implement this together in a couple of lectures. And during decoding, it does not make sense for example, second token to make reference to the third token, which doesn't exist yet, because you're generating autoregressively one token at a time. So it's impossible for you to refer or attend to the tokens in the future. So what you do is you have this specific mask where the similarity scores are set to negative infinity, and the corresponding attention score is set to 0 and never changed. So you prevent the model from looking into the future. And you have these self-attention modules stacked on top of each other, and you have multiple heads. So that's called multi-head self-attention layer. And we made a comparison between RNN, 1D convolution, self-attention, and in the transformer. So this is a new architecture. So we talked about RNNs, LSTMs. Now here's a new architecture called the transformer architecture. Here, we're going to use layer normalization. So compared to batch norm, where you take mean over batch index or batch dimension, you take the mean over data dimension, and given the scalar mean and standard deviation, you normalize data, each data independently, and you also have option to recover the identity by learning this gamma and beta. So this is example transformer block. Upon receiving input, this may be the raw data or pre-processed output from previous transformer block. Doesn't change anything because, and one important thing was these tokens don't communicate with each other unless we are in the self-attention layer. This is the only time they communicate through attention. Otherwise, layer normalization is independent of the data index, which is token index. So is MLP. This MLP is applied on individual token representations independently. Thus, layer norm MLP completely parallelizable during inference and training. So if you stack these transform blocks on top of each other, that's the transformer architecture. Original the paper uses 12 blocks of transformers and 6 attention heads, and we're going to build this from bottom up, starting from tokenizer today. So people say, so this has, yeah, talk about it later. So these days, there are several modifications that people have discovered that works more efficiently, which is pre-norm, RMS norm, SWIGLU, MOE. We're going to talk about these today. So they improve training stability, optimization efficiency, primary efficiency, and scaling behavior. All right, so what are these tricks? And a big disclaimer, I hope I could give you some nice theoretical justification for why these are good idea, but I cannot because they simply don't exist. And people tried many different iterations on improving the transformer performance, and these are the popular choices these days. All right, so in the original form, they call it post norm. You receive X and compute self-attention, and you add that you add the output with X and compute layer norm and apply MLP and add it to the original input and apply layer norm. Let's look at the picture again. So upon receiving the input X, you might have some embedding vector here, embedding matrix here, and you compute the self-attention, and you add the original X with the self-attention output. So this is called the residual connection. You add itself, X and f of X, and the output is X plus f of X. So input comes in, apply self-attention, residual connection, layer normalization, MLP, and here you notice another residual connection before MLP, after MLP gets added together, and then you apply second layer norm. That's the original architecture, right? Okay, so that's called post-norm block. In the pre-norm block, you switch the order. Upon receiving input X, you compute layer norm first, then apply self-attention, then add residual connection, then apply layer norm, MLP, and residual connection. So if you compare before and after, you can notice that it preserves a cleaner identity path through the residual connection. Meaning, suppose the combination of f and ln function wasn't really doing anything. Suppose it's unnecessary. Then you still have option here. If this is unnecessary, there's an option that this becomes identity function through gradient descent if it doesn't add much benefit. So at least you preserve the input. But here, it's more difficult with the layer norm outside for this whole thing to become an identity, meaning y equals x. So here, it's much easier for this guy to be identity. That's one way to look at it. The other way to look at it is if you think about the backpropagation, the gradient flow is less interrupted. So you apply gradient descent here, and dl dy flows to here without any interruption. But here, you do backprop here, dl dy comes in, it has to pass through layer norm, and then pass through x and f of x. So it's more interrupted from, if you think about from right to left, number of obstacles it needs to go through. So what's the change? Move the normalization inside the residual branch, and tends to make the training more stable. So here, move this guy inside the residual. So that's called pre-norm, and it's pretty standard these days. And RMS norm. So if you compare this to layer norm works individually per data, and it subtracts the mean rescales by standard deviation. In contrast, RMS norm removes the mean subtraction step and only rescales it by the root mean square. So here, mean subtraction step is omitted. That's the difference. So what's RMS? norm, you take root mean squared plus some number, small number epsilon, and you divide it by x, and that's it. So in modern LLMs, it's more common to use pre-norm plus RMS norm as opposed to layer norm. If you ask why, I don't know. It works better, to be honest. Okay, so Swiglu is another modern trick that's used in transformer architecture. So if you look at the classical setting, you have input x. And so we're looking at the MLP step here. Okay, so it's so messy. Let's erase everything. So we're looking at this step here. So upon receiving an input, you apply some MLP. That's the MLP step, right? So here we're going to make some tweaks. So input x, apply some matrix, apply value, apply another matrix. So it's a lot of parameters. D by 4D, 4D by D. That's a lot of parameters to learn. And you want to make it more parameter efficient. So what you do is, if you look at this point here, receive input x, multiply with W1. Forget about SNU for a second. And then you do gating here as opposed to matrix multiply. And then you apply matrix multiply finally. So the change is, before we had this part, value of x times W1. Now it's CLU of x times W1 and LLM-wise multiply with x times W2. And CLU is x times sigmoid of x. So it looks something like this. So value is this function, and CLU is, it looks more continuous, something like this. So they change matrix multiply with gating mechanism, and empirically it leads to better optimization and stronger performance. And MOE, I think many of you have heard about this from online blogs or something. So here, there's another tweak in the MLP step. So they want to replace the single dense MLP multiply steps with MOE. What is MOE? So they have what's called a router and a subset of and set of experts. So what is it? So in MOE, these E stands for experts, and say there are E number of experts. So each expert is an independent MLP or matrix multiply layer. And there's another thing called a router, which takes input X and outputs a real number in E dimensions. So what router does is it gives you, so an output of the router is supposed to be sparse, so that it selects top A experts for each token. So number of activations in Rx has to be a lot less than number of total experts. So as opposed to, so in MLP step, you have input X and you output something. Now you're going to have multiple MLPs. And, okay. You're going to have this router that takes X and selects a subset of MLPs to evaluate. So it gives you a soft weight on which expert to use. And the output is top activations. You take top activations in output of the router and selectively apply the expert. So router, it routes to which expert to communicate with, and the top K, for example, top A MLPs get selected, and you do matrix multiply with them, and take average of weighted average of among the selected experts based on these alpha weights. So as opposed to a single MLP layer, you now have E number of MLP layers. So it increased the parameter count dramatically. But in terms of computation, it's not so much, because this is going to be very sparse output. So you're going to select sparse subset of experts to evaluate given X. So in the base transformer model, it had 12 layers of transformer block, a number of heads, and 65 million parameters. And if you compare that to GPT-3, for example, has 175 billion number of parameters. So now it's much, much bigger. And GPT-3 was trained on about 700 gigabytes of data. But recent models like Opus 4.6 or something, it's supposed to be trained on the whole internet. So they downloaded all the text data from internet and trained the model on gigantic parameter model, and it learned the entire internet. Which was impossible before for many reasons. Model wasn't big enough, and they didn't know how to train a really, really large model. All these tricks came in later, and initialization and how to train these still active research area. And honestly, GPUs back then was very crappy. It couldn't support this large parameter model and really, really large data. But now GPU clusters can support this, and as long as you pay a lot of money, you can train a really large model with really large data set, and all of these tricks came in later. So one thing I wanted to cover extra was the decoding step. So this is something we haven't discussed so far. So from here, let's suppose the model is already trained and we want to use it for autoregressive decoding or generation. So suppose we input some text and we have model, and it outputs probability of the second token, probability of next token, etc. And PI stands for prediction of the ith token when the previous tokens are given. So it's a conditional probability of the next token given all the past. That's what these guys are. And during training, we take this guy and apply cross-entropy loss with the actual ground truth output, because since we have the data set, we know explicitly which token followed, and that's going to be the target, and this is going to be your prediction. You have a loss here individually, and sum that up, and that's how the training works, right? So given this trained model, how do you decode, and what are a number of techniques to do better decoding? The obvious thing is greedy decoding. So given some sequence, you ask your autoregressive model, given these as input, what is the probability distribution on the next following token? And obvious thing to do is to do greedy decoding. Take the one with the highest probability. That's going to be your sample. And you repeat this until end of sentence token is generated. And collect all these greedy decodings, and that's your output. That's the simplest thing you can do, right? So let's look at an example here. So you input the first token, it enters your language model. And let's say dog had probability of generation 0.4, nice had probability of generation 0.5, car had probability of generation 0.1. Okay, so we're going to do greedy decoding. So nice is selected, and these branches are not selected. Okay, so now, since DAW is already inputted, the next token, nice, enters as the second. Okay, let me draw this. It outputs some normalized or unnormalized score, and we're showing that. Okay, let me make it more realistic. This guy is most probable, so it gets sampled and enters here. And this guy generates the tokens for the next word, probability distribution for the next token. Here we have woman, house, guy. And this one has highest probability, gets selected, and so on. That's greedy decoding, right? But the thing is, this can lead to suboptimal solution. Can you see which one has highest join probability here? Right, so if you follow this path, dog had 0.4 probability, which is less than 0.5 of nice, but here has 0.9 probability. So here the joint probability is 0.36. Here the joint probability is 0.2. So this path had higher joint probability. So greedy decoding might lead to a suboptimal solution. I'm not saying it's bad, but there are other methods. So one thing we can do instead is what's called a beam search, which I'm sure many of you have heard before. So the idea is very simple. So you keep only the top B most probable sequences. Will this give you optimal decoding? No, unless the beam width is infinity. Typically, this is not infinity, so this does not guarantee optimal decoding, but it gives you better decoding than greedy because it looks longer term. And there's a maximum length on each beam. So here's how it goes. So you initialize a beam. These are previous tokens or prefix tokens. And second number in the tuple is the log probability. And you repeat this process for each sequence in the beam. You compute the probability of the next token. And you expand all candidates. So given the sequence and your token, what is the new updated log probability? It's the previous number plus the current next token generation probability. And you collect all the expanded sequences into a pool. And you only keep the top B sequences with the highest log probability. So you have set of candidates in the beam and candidate sequences in the beam, and this is a width B. Here you expand all possibilities and keep track of their respective joint probability or joint log probability. And then here you keep only the top B sequences in the pool. So many of them will get deleted if they're not in the top B ranking. And these are going to be now your new updated beam. And you repeat this process. And you stop when all sequences hit the special end of sentence token, or the beam length here reaches the upper bound L. Okay, so some of the beams will end early, some of the beams will hit length L, etc. Okay, so this is the case with beam size 2. So here, top 2 candidate here was dog and nice because they had a higher probability than this guy. And for each beam, we expand all choices. And we only need to select top 2 paths because beam size is 2. Here in the second beam, you expand all possibilities. This guy has this guy and this guy has a top 2 highest joint probability. So among them, which one is highest? So we already looked at this together. This has 0.2. This is 0.36. So this guy is in the top in the beam search. Another thing you can do is very simple. So as opposed to greedy decoding, you find top k probable tokens. K is a prefixed hyperparameter. So you only expand the top k tokens and you sample the next token and we repeat this process until the end of sentence token is generated or you hit the length limit. And here's a pictorial view. So given the prefix or context, this is the probability output predicted by your LLM. And here in this case, K is preset to 6. So you're only going to look at top 6 candidates. And you're going to sample from these top 6, I guess, unnormalized logits because you only select a subset, so this is no longer normalized. But among this, you sample, so these no longer exist in your universe. You're only going to sample according to the logits in the top 6 outputs. Okay, so here, let's say, I don't know, this guy is selected, and it gets inputted into LLM, and you have prediction for normalized prediction for the next token. And here, we're only going to look at top 6 candidates. So these guys cannot be sampled anymore. and you sample according to this normalized logic, and next thing gets sampled. Another thing is Euclid sampling, and has some threshold eta, and I think it's easier to explain with the picture. Here, the hyperparameter eta is set to 0.92. So as opposed to having top k, now you have top logits, so that it sums just over this eta. So here, if you include all the way to house, now your sum of the logits is going to be 0.94, and you're going to sample from these top logits that sum up just above eta. Same thing. Now here you're only going to sum up until these 3 points, and all of these are going to be deleted. So here is example generation from GPT-3. So you input these as the context, and then you start generating one token at a time, and that's an output, and it looks very natural and human-like. So I'm not sure if I'm going to have enough time to cover lecture 5. Anyways, so another thing that's very important in development of these language models is incorporating human feedback. So say you download the internet and pre-train it in a language model auto-regressively, and you're going to gather, to improve its performance even more, you're going to gather human feedback on its generation quality. And you're going to ask human to rank various generations. And you're going to train a separate model that predicts these humans' annotations. So once you have collect enough human samples on these rankings among generated data, this model is going to mimic human behavior and output a ranking as if human has labeled its generation quality. And given this trained reward model, you're going to fine-tune your language model so that it not only minimizes the generation error, which is maximizing the log likelihood, it also incorporates loss respect to this guy. So it wants to have high ranking output from this trained fixed reward model. That's the high-level idea. So you input something to the language model, and here you generate multiple versions of the output. And humans are asked to rank these various outputs from 1 through, I don't know, 5, or for 5 outputs or something like this. And then we're going to learn a preference model that mimics the human behavior. So we're going to ask humans to rank them, and this reward model learns how to rank various outputs. Because humans are very expensive and slow, so once you collect enough data, we're going to replace them with the model. Once you have the model, now your learning objective changes. One is that we're going to learn the definition of KL divergence between two probability distributions in the upcoming lectures. But right now, just think about it as some loss between, which captures similarity between two probability densities. By the way, this is not symmetric. So this is input 1, input 2. If you swap the order, you get different output. So it's not a valid distance metric. Anyways, so intuition-wise, you can think of it as distance function for now. So what you do is here you have the pre-trained LLM. This is fixed pre-trained model. This is your new model that you want to update. You don't want, so here it penalizes if they shift in probability distribution. So you insert some context, it's going to output a probability distribution on the next token. And if they defer too much, then you get penalty. So all this loss is saying is you don't want to change too much from your pre-trained fixed model. You only want to move slightly. Here you have another loss, which comes from the reward preference model. So if you generate some context, this reward model is going to evaluate your output, give you a preference score, and you want to increase the reward also, while not moving too much from the original base model weights. So this is frozen. Gradient doesn't flow here with a special node in PyTorch called stop gradient. If you have this before any module, gradient cannot flow through this. It gets blocked. So this guy doesn't update. It only flows through here. Okay, this is fixed as well. All right, so in the remaining time, okay, let's just do as much as possible then. I'm going to open up my laptop. Is this too small in the back? Too big? Too small? This too small. How about this? You prefer this one or this one? 1, 2. Okay. Okay, so I have some extra stuff here, but TAs have told you to copy the zip file from ETL to your personal Google Drive. How many of you have not done so yet? Okay, I'm gonna just walk around and make sure everybody has it up and running. Once you have it up and running, please connect to your Google Colab. This should be turned into a green check mark. And make sure you can run the cell. Here you're going to need to give permission to Google. So Google Colab gives you a free GPU, so we can do this exercise together. So for those of you who never use Colab, this is an interactive notebook-style coding platform where this computation does not run on your local machine. It runs on one of the random Google's GPUs and just gives you the result. And let me just walk around and see if I see all the check marks. So yeah, one of the if you get an error, you might want to change your path to where you pasted your stuff. So for me, I'm at my drive, Deep Learning 기초 26, lecture 5. So you probably need to change this to wherever you copied your files. Does Colab work on iPad? Yes or no? It does? Okay, it's good to know. Okay, how many of you are stuck? I noticed about 15 people downloading zip file, so I couldn't see until the end. Anyone need help with step 1? Okay, so answer file is going to be uploaded after the lecture. So don't sweat it if you get stuck somewhere and fall behind. So today is going to be the first lecture of this Building LLM from Scratch series. First step, of course, is going to be dealing with the raw data and pre-processing the data so LLMs can take it as input. And this whole thing is called tokenizer. And we saw a very, very brief example last time with only 4 characters in the vocabulary. But for example, if you want to do character level, you need at least 256 characters in the vocabulary. And if you want to do word level or some intermediate level, you need much larger dictionary. And towards the end, we're going to learn one of the famous techniques called by-pair encoding, BPE in short, and load in previously trained word embedding and try to visualize it by down projecting the embedding vectors to 2 dimensions. Okay, so here, this step, it mounts your whatever's in your drive folder to so that Colab can read what's inside. And here is a very brief language model introduction. So LLMs are neural networks, that, like we saw in the transformer lectures, that's used to predict the next word in the sequence. So for example, if you enter hello GPT, explain yourself, it starts to generate 1 token at a time. And we just covered various decoding techniques, and we can do greedy, beam search, nucleus sampling, top K sampling, whatever, and starts generating 1 token at a time. And as soon as generate 1, it gets inserted back into the model to predict the conditional distribution of the next token given all its past information, and samples next token from the conditional probability and gets entered to the model again and generates next token, etc., until you hit a special end of sentence token, or until you hit maximum decoding length. So how does LLM know how to interpret these actual English words? Because as you know, computers only can handle numbers. So we need a mechanism to convert these English words or characters into a number so the machine can read it and understand. That's where tokenization comes in. So what's a tokenization? So it's a process to text it's a method to process text with the neural network to convert the text into numerical form and back into text. So for example, if we insert this string, tokenize string hello ChatGPT, it first parses the string into a list of interpretable atomic representations. It could be word level, character level, or something in between. And each atomic representation gets converted into a number that corresponds to an element in the dictionary. So this 1 means first word in the dictionary. This 4 means fourth word in the dictionary. So there's a visualizer, interactive tokenization example for popular models. And let's see if the college Wi-Fi will allow me to open this. So let's see. Let's, for example, look at GPT 4.0 or GPT 4, and you insert something here. So here, you first breaks the input, it parses the input, and GPT-4 uses a specific tokenizer, and this is the corresponding token IDs for these sub-elements. So U gets turned into a number 2675, R 527. Do I have a same thing here somewhere? User assistant. I don't know. So my gets converted into 2465. Same thing here. Name 836. And if I change the tokenizer to, for example, QN 2.5 model, then they parse it, and individually all these things get mapped to different numbers. So different models use different tokenizers, and you can try to play around with this in your free time. So we're going to build a tokenizer for, I think, Shakespeare dataset today. But I don't think, due to time constraints, we'll have time to get there. But let's try to go as far as possible. So this is what the output of tokenizer looks like. Input string, output a series of numbers, so that the machine can understand the language. So we're going to introduce an ABC abstract base class, which defines different methods with nothing implemented yet. And you're going to implement all these methods yourself. So what does it have? So it's a tokenizer class. It's a ABC meta class. So for example, so in case you don't know what abstract base class or any concept of class, don't worry, it's not important. But it's nice to know. So you're supposed to inherit from this and implement each function details later. So this just gives you some framework to work with. So in the member variable, it has vocab, the vocabulary, and inverted index. I'll explain this later. And has train method, encode method, and decode method, and save load. So the train method, it builds a vocabulary from a given corpus. The corpus is a data set. So let's say you downloaded a bulk of data from Wikipedia, and you want to build, first thing you need to do is build your dictionary or vocabulary. That's what the train method is supposed to do. Encode, upon receiving some random string, is supposed to parse it and turn this into a list of integers, like you saw in the, what is it called? Voxelizer? Yeah, tokenizer. Okay, and decode is supposed to input a list of integers and turn it into strings so that humans can verify what these numbers are in English. So it does the reverse. And you have basic save and load. And I guess the most naive approach is to split the string into by checking these spaces in between the words, and first parsing the input string based on these spaces, breaking them down into list of individual separate words, and giving for each unique word in this parse representation, give a unique number. So, for example, if this is our entire corpus, then each unique word here will receive a unique number, integer number. And for example, if we insert a string of welcome to class, then our tokenization result will be just look up the corresponding hash table entry. Welcome is number 0. So we have first representation is 0. 2 is number 1 here. Class is number 5. So this string, once we build this corpus, and once we build the corpus, that's fixed throughout. Once we build this, and upon receiving some string, gets converted into a list of integers.